I'm just going to tell you right now, we're going to start with wires, and then we're going to move on to components. This is the MC. We're going to start with wires, and we're going to talk about the internal resistance, the resistance, the AC resistance. Then we're going to talk about the AC inductance, the DC and AC inductance. This is chapter 9. We start with wires. We assume these wires have a circular cross-section. There doesn't have to be one wire. We're going to start with one wire, but most of the time you get braids where you're going to have multiple wires that are woven together. And the reason for that is if one breaks, there's still conductivity. And the second thing is for high frequencies especially, they have much lower resistance compared to a single wire because the overall perimeter of all these wires for the same amount of cross-section is much bigger. When we have a wire, generally speaking, we have something with a radius A and has a length L and a conductivity. Usually the conductivity is copper, almost always. Sometimes it's actually steel, but it's going to have a conductivity. And I'm doing it for a copper wire. Matter of fact, why don't I do this? I'll put a given sigma, and it's going to have a given mu relative. That way I'll cover all bases. And what I want to know is what the equivalent resistance is of this R for DC and R AC. Well, for R DC, if you remember, it's always proportional to the length, and it's inversely proportional to the cross-sectional area. So it's pi A squared, and if it was some other shape, like if it was a square cross-section, it would just be the area right there. You all follow me? Whatever the cross-sectional area is. And we assume the cross-section doesn't vary versus length of the wire. And then it's divided by the conductivity. Now that's the DC resistance. Next, we take a look at the, what I call AC resistance or high frequency resistance. So for the same wire of a given length L with a radius A, conductivity sigma, mu relative here. Now we have to say if the key parameter is skin depth. And the skin depth is defined as 1 over the square root of pi f mu sigma. Now remember that mu doesn't have to be mu naught. Mu is mu relative times mu naught. And you will see in 1045 steel the mu relative is 1,000. So it's a substantial effect. 1045 steel has a much smaller skin depth in general than, it will have a smaller skin depth for a given frequency than copper. So that's the skin depth. Now, if the radius, and these are the assumptions, if the radius of the wire is going to be greater than the skin depth, then what you're looking at as far as the area that the current penetrates, this is the radius A. The actual current will penetrate an area of the skin depth thick on the surface. This actually is it's an accurate assumption. An accurate way to get this. If you actually do a formal integral of the value of the current density versus the area of that wire, and you include the skin depth effect, which is really 1 over alpha, you get exactly the same result. So if that's the case, all the current flows through this purple area. It flows on the surface of the wire.
How could you have skin depth greater than A?
Sure, DC. You don't know what the skin depth. If it's low, if the skin depth is greater than A, just assume it's DC. That's the easiest calculation. Okay. For this, now this is the R, and you can call it high frequency or AC. So R high frequency will be R AC for alternating current, and that's going to be proportional to the length, inversely proportional sigma, but now the area is pi A squared. So it's the total area here, but you subtract from it the inner area. So it's that minus pi, and then it's going to be A minus the skin depth squared. Now this is an exact formula. So if you break this down, you get L over sigma. And then if you look at this, the pi A squared gets kicked out. If you go ahead and square this, you get pi times A squared, right? Well, there's a pi A squared there. It's gone. Then you have minus pi A times skin depth twice. So you get 2 pi A skin depth here. And then you're going to have actually minus pi times the skin depth squared. Now that's exact. And that would be in ohms. I didn't put the units down here, but this is in ohms as well. Now, if the skin depth is much, much less than the radius of the wire, which is the case for a large number of types of problems. We're talking about high frequency. If that's the case, then the R high frequency equal to RAC is approximately equal to L over sigma and 2 pi, and then it would be A times skin depth. Let me tell you where this comes from, and so you can remember it. Now, what it's really saying is, and this would be in ohms, if we took this and cut it right there, and then we stretched it out and made it one long piece, it would have a thickness of a skin depth, this should make sense to you, and it would have a length equal to the perimeter, or 2 pi A. Just cut it right there and bend it out. The perimeter is 2 pi A, right? Thickness is a skin depth. This is effectively the same thing as that shaded purple area there. So that's where this comes from. And you ignore this delta squared because if, like, the skin depth is 1/10 of the radius of the wire, that's 1/100th of the prior value without A even. So you can ignore it. So that's the high frequency resistance. And this is something you need to know. You need to know that, and you need to know this. And you need to know this. So these are critical that you know. Now we're going to talk about the internal inductance of the wire. Still, skin depth is the same. Now it's inductance. I'm going to change this symbol and call this script L here. So now when we talk about the inductance of wire, we start with the DC inductance. And this is internal, by the way. This means it just has to do with the inductive energy inside the wire, nothing outside. For the DC inductance, for a solid wire of radius A, and I'm going to use it length L. Usually you do this in a per meter thing. Conductivity sigma, mu relative, you're going to see that this is a straightforward one. Now, we could assume a current density flows through there. Say I divided by the cross-sectional area would be the current density. We can assume it's uniformly distributed, and then we could use Ampere's law to calculate H at a given radial distance. Then we could take that and say 1/2 mu H squared would be the magnetic energy density and integrate it over the whole thing, and then divide that by I squared to get the actual inductance. I'm just telling you, you could do it this way. The formula, I'm not expecting you to do it, would be a double integral, 1/2 mu magnitude of H squared over the volume integrating, and this would be over the volume of the wire, and that would be equal to 1/2 L DC I squared. At the end of the day, if you look at LDC, you write this down, and this is going to be per meter, is really mu over 8 pi henries per meter. Now, what is unique about that compared to the resistance calculation? It doesn't depend on the dimensions. All right, length, this is a per meter thing, so it is per length, but it doesn't depend on the radius of the wire. It can be as big as you want. You also notice it doesn't depend on conductivity. It just depends on mu. The assumption is the wire is homogeneous. It can't have a varying conductivity or anything. So that's the DC inductance. The AC inductance, we could prove by assuming all the current flows in the skin depth, and we can do this one, but it's a little tedious. I'm just going to give you this, so write this down. And this is all internal, by the way. This is internal DC, this is internal high frequency or AC inductance. And that would be L high frequency is equal to L DC, and then it's 2 times the skin depth over the radius A. Internal inductance is shown as mu L over 8 pi. If you get rid of the L, it's in per meter. And then he shows you the AC is mu over 4 pi sigma over A. And typically what I like to do is say it's the DC resistance times 2 times the skin depth over A. Please mark this down so on top of page 505, equation 96, but I'd rearrange that formula and do it this way because there's less memorization. Now, something to note here, what happens to the high frequency inductance as frequency goes to infinity? If it goes to 0, what's the internal inductance? It's 0, right? If skin depth goes to 0, just look. 0 times anything is 0. That means there's no internal magnetic energy. Literally, as it goes to infinity, less and less energy is inside, everything's outside the wire. Now, I remember when I did my master's and I was working with plasmas, I was working for a guy named Stack, and we had this plasma etching chamber, and it was about, I think it was 3 kilowatts, but I don't remember. I noticed that all the piping that conducted the electrical power to the chamber was hollow aluminum. They'd run water through it, a coolant I should say. I think it was Freon through there to cool it. I realized the reason it's hollow is because it wouldn't matter if it's solid. The inside portion carries no electrical current. Everything's on the skin. Internal inductance, high frequency and DC, and internal resistance, and it's both for DC and for high frequency. So now we get into elements. We're going to talk about what a real resistor looks like, and a real inductor, and a real capacitor look like at higher frequencies. And this is real important because most of the equipment you work on, especially with amplifiers and stuff, are designed for what I call low frequency operation. But oftentimes they get pushed into the high frequency range by necessity, especially with these amplifiers that are like class A, B, and stuff like this, where they're at higher frequency and they're pulsed. A resistor at anything at low frequency looks like the element you want it to look like. So a resistor looks like a resistor at low frequencies. At low frequencies, they all should look like that. But what happens as frequency goes up, there are two effects. The first is you're going to have a voltage difference here, and you're going to have a current here, the voltage difference. Anytime you have a voltage difference between 2 points in any region where there's proximity between the voltage difference, you have an electric field necessarily that occurs, something like that, that will be mapping out, these would be field lines, everywhere around that. That electrostatic field or pseudo-electrostatic field has energy. That energy is associated with a capacitance. You all with me? So what we do is we model that by a capacitor. I'll talk about how to calculate it. Or usually it's given because this class, they'd have to give it to you. But if we have a resistor R, typically we have a capacitor C to account for that. The resistance is the main thing that's going to limit current flow in the straight wire. But anytime that you have a wire and you have current flowing in it, you have a magnetic field around it. You both have internal and external magnetic field. Anytime you have magnetic energy in a system that is not propagating away, that can be considered localized, then you have inductance. So now we're going to have an inductance. And what they usually do, almost always, is say this inductance will have this symbol, but they'll call it L and the sub will be ELAD because it's for the leads. So now if you look at the impedance between A and B, we'll do this in the S domain. You can say the Z, the impedance of this actual resistor, is a function of frequency S. And S is J omega plus sigma. I'm doing it in this domain because it'll be a little less complicated. If you look at this, it's got to have SL, right? Because the impedance of an inductor is J omega L, or in this case, SL. Remember when you did Laplace analysis of circuits, use SL for the impedance of an inductor? This capacitor will have 1 over SC impedance, and the resistor is just R. So if you looked at the total impedance of this as SL, then it's plus 1 over R plus SC. Now the only thing I'm doing there is taking 1 over the first impedance plus 1 over the second impedance, take 1 over the whole bunch. Depending on what you want to do with this, I can multiply top and bottom by R over here, and now I get R, and I get 1 here, and that's the impedance of that system. So in his book, at the bottom of page 508, that type of a circuit, but he does one thing. He calls it L sub L is lead and L sub X is internal. Almost always, any internal inductance associated with this resistor is negligible. So you can chop off that L sub X. This is the model everybody uses. It's a single inductance and it's associated with the lead. So a check on all these models is if S goes to 0, if the frequency goes to 0, it better look like just the element you're trying to model. So if S goes to 0, Z of 0 here is simply R. That checks the box. It looks like what it should. If we go ahead and we replace S just by J omega or J omega by J 2 pi F, I'm going to show you what the plot will look like. What you'll see is this is the way they're always plotted. They're Bode plots. So on this axis, they plot the log of F. Or you're going to get stuff like this. And then and so forth. And this might be 10, 100, 1,000, 10,000, and so forth. Got me on that? That's a logarithmic scale. On the vertical axis, it's logarithmic 2. It's log on the vertical axis, and it's log of the magnitude of the impedance. But usually they put a 20 here so it can be in dB. So for a resistor, it will look like this. This value will be 20 times the log of the actual resistance. Then there'll be the first, and I call it a cut frequency, or the first frequency where it starts going down. And it is a result of this right here. And if you get rid of that R and put 1 over R here, it is when SC equals R. You with me? Because that will be when these two values become identical. Y'all with me? I want you to just watch this. So if I take 1 over R and I equate it to J, or in magnitude, forget the J, in magnitude, 2 pi F times C, you can see that this frequency, the cut frequency here, is going to be equal to 1 over 2 pi R times C. And that's the frequency. Well, all of a sudden this right here will start going down at 20 dB per decade. So here, this frequency is going to be 1 over 2 pi R times C, and this is called, I'll just call it the low frequency, 3 dB point. And it's going to start going down, but it's going to hit a second frequency. And the second frequency is when all of a sudden this impedance and this impedance, the same magnitude, opposite signs, that's an inductor, resistor, and a capacitor, and we call that resonance. So resonance occurs right here. And you can call this the resonant frequency, or FR, and that's equal to 1 over 2 pi square root of LC. Now that L is the actual lead inductance, and C is the parasitic capacitance. That should make it a point here. This is a parasitic. Parasitic, something unwanted. It's a parasite that literally bleeds current, causes it to behave in a way you don't want. And then after that point, the inductance takes over, it starts going up. The height of this, or the slope, is going to be minus 20 dB per decade. The slope of this is plus 20 dB per decade. This is shown. It's not a Bode. What he does is show you this. I wish he would have put a Bode. He shows you the actual values. Now remember, you don't have to put the 20 there, but typically they'll put 20 times the log of that. That way it's a true Bode. This is not a Bode, that's from measurements, you know. Typically, in the stuff I'll give you, I will show you a Bode because that's almost always used. And if they say it's 20 times the log of R, then this will be in dB. Y'all follow me? If it's not, then you're going to get these gyrations and it'll say ohms. Either way, that's the plot. So that's a resistor, what it looks like. When you think of resistors, you normally think of these, what, 1/8 watt, 1/4 watt resistors. They're round little barrels with color codes on them. So now inductors. It's shown on page 511. He shows some examples of inductors. When you have inductors, just think of a coil of wire around a core. That's all it is. I mean, transformers have both internal and mutual inductance between a primary and a secondary core. And you can model them as either a magnetically coupled circuit or a transformer with different values for the different components. But inductors are used a lot for the old classical way to tune circuits. Do you remember that you would have a tank circuit, a parallel resistor and capacitor, and you see these arrows through one of them, so you could vary the actual value in tune like a radio or something. You change the resonant frequency. Whenever you have a parallel R and C, it looks like an infinite impedance at resonance, right? So what you typically do is tune that with an antenna. And at resonance, it looks infinite. It develops the open circuit voltage. You can pull it off, and then you can go ahead and demod it and everything like that. But that's what that tuner was for. And if you looked at old radios or anything, you see these capacitor plates that move in and out. They're like plates that they look like almost 1/4 of a pi plate to 1/2 of a pi plate. And they'll have slots where they interleave, and you tune it, you get more capacitance, pull it out, you get less, and that's the way they tune. They have an inductance across that. Doesn't matter what makes the inductor, and some things have a lot of inductance you have to account for, just wires running around. And it has internal inductance and has external inductance you have to account for. Normally an inductor is shown like this. Now, anytime you have wire, inductor has a lot of wire. You're going to have, remember, the inductor itself is made of wire. Well, wire actually has resistance. We just saw that, AC and DC resistance, and it can be substantial. But this is inside the inductance because most of the wire is wound there, and you try to keep your leads as short as possible. So then they're going to model this as a resistance, and this is called a R parasitic because you would not want that. And then the whole thing outside here, you're going to have a capacitor. Now remember, this is internal, so there's going to be a plus to minus voltage from A to B shown here. So whenever you get that, the plus to minus voltage, if current goes through it like here, then you're going to have to associate it with a capacitor. And this is the parallel capacitance, or a parasitic capacitance. Let me see where that is. Well, he has the figure I'm talking about. This is on figure 911. He calls it C of X and R of X. But those are parasitic. Now, if you look at this, just as we did the last one, we're going to write down an equation for inductance. But I want you to see this. This has an inductance value of simply 1 over CS. The capacitor has an impedance of 1 over J omega C. You replace J omega with S, that's it. Over here, what's the inductor? Just SC, right? And the resistance is just R. Maybe I should put C parallel above this, or C parasitic. All right, so how do you get the impedance of this? These two have a combined impedance, I'll call it ZLR, of simply SL plus R. And I'll leave off the parasitic. So if I look at the actual impedance of these two, Z for this inductor is a function of S. It's 1 over the first one, so it's 1 over 1 of the first one, or CS, plus 1 over the second one. So that's 1 over quantity SL plus R. Now I like doing it this way. You can multiply this times that and divide by the sum, but I do it this way. The next thing is, what does this thing actually look like? Let me see if I can simplify this. I'm going to multiply top and bottom by SL plus R, so I get SL plus R here, and then I get 1 plus, and then it's going to be CS times SL plus R, and that's going to be equal to SL plus R over 1 plus L times C times S squared plus RCS. So if I take this and I divide everything by LC, on top, I divide by LC, I get S over C, that's plus R over LC, and then I get S squared plus R over L times S, and it's plus 1 over LC, I'm sorry about this.
Up top, why did you just do CS plus 1 over? Shouldn't it be the resistance of the capacitor is 1 over CS, correct? So why did you just do CS instead of?
This is 1 over 1 over CS. That's CS, isn't it?
Gotcha.
It's 1 over the first impedance plus 1 over the second impedance. That's what I'm doing. All right, now on this one, you're going to see something that's interesting. What's the impedance of an inductor at DC? When S goes to 0, what do you actually get? Those two go away, right? But what happens here? You get R, right? You know why? Because I put a value of R associated with the resistance of that wire in series. Now, if that's very low, it will go to approximately 0, but not actually 0. Now, if you keep on going up in frequency, one thing you notice at high frequencies, the S squared in this LC, that will be the part that will cancel. That's called a resonance. When S squared equals LC, or S is square 1 over square root LC, S is 2 pi F in magnitude. So really for an inductor, which is different than the other one, you don't have a low frequency cut-in per se. This is the typical plot you associate with an inductor. If this is the log of the frequency, and this is going to be 20 times the log of the impedance of the inductor here, what actually happens at very low frequency for an inductor, you're going to have something that looks like this. It's going to be very low. This is going to be equal to 20 times the log of that resistance. And it will have an 8, but it'll be standard, it'll be constant. Now, where that actually starts changing and it starts going up, here, when you have S over C equal to R over LC, the C's cancel and you get S is equal to R over L. And then S here would be 2 pi F. I'm replacing, normally I put a J omega in there and equate it in magnitude here. But when you do this, this will be equal to R over L. Remember, that's the resistance of the wire internal, and it is an AC resistance generally, so it changes with frequency. And you see that the actual first cut frequency, or the lower 3 dB, he does not have this in the book, will be equal to R over 2 pi L. I want to say this is usually very low. Usually the resistance is of the order of tenth of ohms, maybe less, and L is of the order of millihenries or microhenries. Y'all follow? It's a very small value. So normally we ignore this, but it'll go here, and then it'll start going up at a rate of plus 20 dB per decade until it hits the actual self-resonant frequency, or resonant frequency, which is 1 over 2 pi square root of LC. And then it'll start coming down at minus 20 dB per decade. So the real thing you worry about is this. Everything on this side of the self-resonance is increasing by 20 dB per decade. Everything on that side is decreasing by 20 dB per decade. And when you put it in the actual resonant frequency, this cancels that, and then you can evaluate that to find out the peak value. All right, that's an inductor, high frequency of an inductor. Now we look at a capacitor, and then I talk about multiple wires. Now there are two different kinds of capacitors to consider. One is called an electrolytic capacitor. Anybody want to tell me what an electrolytic capacitor is versus a regular? What are some of the properties and uses? An electrolytic capacitor is a capacitor that will, generally speaking, store a lot more energy than a non-electrolytic or something with a solid dielectric. The dielectric or this are kind of gooey, and if you ever cut one apart, you'll know what I mean. Sort of a white goo, as I remember, for the smaller ones. But they can store a lot of energy for a given volume. So with an electrolytic capacitor, you're going to have stuff, dipoles are in here, but they have plus to minus charge centers, and if I put a given voltage, I'm going to put the negative on top here. If I put negative, positive, they'll align themselves so the positive centers of these dipole centers will be up this way and the negative will be down here. Now, if I changed the actual polarity, these things would flip, and they can flip. They can literally rotate. That rotation causes heat. Now what happens is, if you have an electrolytic capacitor and you don't have a DC voltage, you can have like a DC voltage with noise, with some sort of an AC superimposed on it. As long as the polarity doesn't change, these dipoles will always be oriented in a certain order, either up or down. But the minute you get something here where the dipoles will try to flip, now it starts heating and these things blow up. And I had an experience with them. I wasn't there when it blew up, but I saw the after. These are high energy electrolytic capacitors that are used for rail guns. And you can never allow current to go through one of those in the wrong direction. You can't let the polarity change. And if it does, you get what I saw. It looked like a grenade. The whole front end blew off, and whatever was in front of it really got clobbered. Nobody was there, but it blew up because they discharged it. There was nobody in front of it. And it's lethal, it can kill you. You've got to be very careful with large high energy capacitors because of that. They are electrolytic almost always. You can never put a polarity that would reverse with because there's an enormous amount of heat that's caused by this stuff. You just can't. That's an electrolytic capacitor. The other kinds are the ones where the dielectric is it's solid, like mica, for instance. These are the little disc capacitors, but they can be large or small, and they generally don't store as much energy for a given volume of space. But something about these two is you can get these, and you can have a fairly high breakdown potential to break these down. Anybody remember what the breakdown potential is of air in terms of volts per meter? What electric field would cause an arc to begin? Gannon, do you remember that?
3 million.
3 million volts per meter, 3 megavolts per meter. That's about what it takes to initiate what's called a stepped leader. Y'all seen lightning, right? So if you're on the ground and all of a sudden, remember, if you have negative charge in the cloud, you get positive induced charge. The lower one's negative always on the thunderstorm. You get positive charge induced in the ground from imaging, and you'll start building. All of a sudden, you get a larger and larger value of electric field. When that electric field goes over a certain threshold, which is 3 megavolts per meter, and it's very easily done if you have sharp points because you get field enhancement around there. Then you get something called ionization. And if there's enough charge under there to support a current, you will just see this thing shoot up. It's called a stepped leader, a little filament, until it gets the stepped leader from the cloud or gets to the cloud negative center, and then all of a sudden all heck breaks loose because that's an ionized channel, and now there'll be a direct short for the other current, and it will heat up and expand, and you'll get a huge amount of current. Peak currents on cloud to ground lightning from the lower charge center to the ground are about 20 kiloamps per meter, but they go up for super volts, and means you might as well know this because, Hunter Birch and Clint Snyder, they work in this arena. I did it one time. If this is the Earth, typically you have a low negative charge center here in the cloud, and that is typically at about 6 kilometers, roughly, the height. But then up here, about 10 kilometers high, you get a positive charge center. You can look this up. And usually these two are about the same. Now the most common kind, think about this, the distance difference here is 4 kilometers, right? The thing that's separating this charge is rain or graupel or hail. Graupel is just slush. Rain, you know what rain looks like, and hail, you know what it looks like. So this stuff's falling, precipitating. And it just like, you ever did the thing where you take a balloon, rub it on your head, and put it on a wall? Charge is induced in these things, and it tends to pull negative charge from this upper cloud and deposit it here in the negative cloud. This one induces a positive charge here. The positive one induces a negative charge, just as we talked about, right? Usually the lightning is here, the cloud, intercloud lightning. That reduces the value of each and reduces the likelihood of cloud to ground. But here's what happens. The charge centers also have wind. So as wind happens, you get negative, 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 positive, positive. Now, sometimes, actually, it's still usually this that happens. There's usually a cloud to ground strike, but you notice that positive charge center up there, right? And this is a wind field, so wind's blowing it this way, but if you know anything about a thunderstorm, there's all sorts of current that goes this way, that runs under the storm and towards the center of the storm. It's just the way it is because it's cooler there, so the air rushes in. Then it goes up, so you get all sorts of weird wind shears and stuff like this. But every once in a while, and this is the danger with dying thunderstorms, this thing will go way out in front. And then you'll get cloud to ground lightning from the positive. That's called a superbolt. And those can get to be 270 kiloamps peak. Now that's deadly. At that point, the small plane, if it gets hit, or a glider, usually gets taken down. They won't get taken down with the peak for cloud to ground typically is 20 kiloamps. It might get 25 or 30 occasionally, but it would be rare. But when you talk about 270 kiloamps, especially the duration of the pulse, that's an enormous amount of energy. And if it hits a small, like you know what gliders are, right? Any plane that doesn't have a serious amount of grounding protecting against that, it can take it down because it can cause heating in the superstructure, and there'll be failures, especially with these super light composites that they have. They can just explode. That's the one you worry about, is that huge it's called a superbolt. You guys got phones, just look it up. Why did I say all that? Because with capacitors, it's important to understand the type of capacitor. This is just a lot about type of effects here. If you're going to do shielding, you have to know the threshold or voltage you might be dealing with. You should have some awareness of this if you get out in the real world and you're dealing with the aircraft industry. For capacitor, what's the model of a capacitor? Well, as with any element, you start with the element. At low frequency, a capacitor has to look like a capacitor. Now, if it was an electrolytic capacitor, you would have a resistance, and this would be an R, and this is really, it's a leakage resistance. There would be one there, because remember, with an electrolytic capacitor, it's made of that goop. It will leak a small amount of current. It's meant for power supplies if you want to get rid of ripple, stuff like that. The power supply, if you have a full wave rectifier, if you think about that, on the output of that, it always has the same polarity. You put these capacitors on output of a full wave rectifier, you don't care if you get a little leakage, as long as it isn't a lot. And then you're always going to have an inductance because of the leads. That would be for an electrolytic. The model we use always, because we don't deal with electrolytic capacitors typically, is this. You start with a capacitance, then you're going to have, doesn't matter the order you show this, it could be, and this is going to be a resistor, and that's a parasitic resistance, or it's unwanted. You'll have R of X, and then you're going to have actually an inductance that's parasitic as well. And now they want the impedance of this from here to here. What is the impedance of this? And I'm going to use S. So it's going to be equal to SL, forget the parasitic, plus R plus 1 over CS. What is the impedance of a capacitor? And you'll notice I got rid of this leakage resistance. What's the impedance of a capacitor at DC? Think about it. It would be infinite. Technically, he was right. If it's an electrolytic, it would be R. And here's the plot you get. We can get to the resonant frequency. What happens is you're going to get something, and the thing is going to come in at the self-resonant frequency is going to be 1 over 2 pi square root of LC. This is going down at minus 20 dB per decade. This is going up at plus 20 dB per decade. And this is going to be either 20 times the log of the magnitude of Z capacitor, or it'll be just log of Z. It'll be one of the two. But that's the actual trend. That's what's called the signature of the impedance. And this is shown in his book. And what he does is show you actual measurements on page 515 if you want to write it down. We've covered the different elements. We've covered L's, R's, and C's at low and high frequency. We covered the wire internal inductance at low and high. And we covered the actual resistance at low and high. Now what we have to do is talk about, well, what happens if you have more than one wire in parallel? In general, if you have wires that are in parallel, they call it twisted pair typically, or braided wire. You're going to have a certain number of wires. Now each of those wires is going to have a certain resistance, right? Do you all agree they're in parallel? So when you're dealing with wires, it could be an AC, it could be a DC, but normally what you think about is you're going to have R, and this is going to be for a single wire, I'll call it RW, but you're going to have so many of them, and they're all in parallel. All these things have RW, and it doesn't matter how many. That means the net effect is what? Is going to be the resistance of one of these wires, right, divided by the number of wires. Do you all follow me? Because they are in parallel. Everybody with me? What happens if you have inductors? If we talk about the inductances, remember how to add inductances in parallel? It could be AC, it could be DC. I'm talking about inductances. If you have that many wires, again, doesn't matter how many, but if you have a total of N wires, each with L per wire, what is the inductance of this look? These look like what? Just individual inductors? I could show that. But if they're all in parallel, what happens? L wire, L wire, L wire. Class, what are inductors in parallel? Total inductance is divided by the number, right? This is going to look like a single inductance, L of the wire, divided by the number. What about inductors in series? You want the equivalent, just add them up, right? Well, resistors in series, you add them up and replace it by that. So when you get these wires that I'm going to give you data sheets that are actually real data sheets, and they'll have a certain gauge wire that you're going to have to find out what the diameter and then get the radius of the wire, and it will be in mils, so you have to convert that to meters. And then you're going to figure out how many are in parallel, and you're going to figure out either the resistance or inductance or impedance of the Friday. What's on the quiz? I'm going to give you something related to this. Wires, multiple wires, AC, DC, all right, or resistor, capacitor, inductor. I'll let you take one 3x5 card and put formulas on it. You can write on both sides, take a full sheet of paper and just minimize it. I will give you mu naught and epsilon naught. I'll give you the conductivity and permeability of any material and epsilon relative. Now on Friday, what I'm going to do is go through digital signal analysis. I'll talk about the actual grounds. What is your interpretation of a ground? It's a zero potential point, and it's related to either a chassis, and that's some kind of something where parts are mounted on. The chassis can have a zero potential. It's called a chassis ground. It can be an earth ground. That's where the earth itself is assumed ground. And the chassis ground, the earth ground, can be different for one reason, because there's actually wires connecting, and the current that flows through there will cause a voltage difference between the two. And there's something called a signal ground, and that's like if you have a chassis, say a metal box that has a ground where things are measured against. But then you have chips themselves. Each one of those chips has something called a signal ground. And the signal ground, the chassis ground, can be different. And there are methods to actually locate and connect grounds to prevent something called ground loops or unwanted effects. Basically, especially with lightning and stuff like this, called world-class problems. I'll just tell you this.
Ground bounce.
What?
I heard it called like ground bounce.
There is a ground bounce problem, but here's the worst problem in my opinion. This is for stuff exposed to the elements. But if you have an earth ground here, now an earth ground, the symbol is this. Right, that's a symbol for an earth ground. Have you heard of these? These are long grounding rods you pound in. Does anybody see the solid? They're solid. You buy them up at Home Depot or at Lowe's or something, or Ace Hardware. All right, if you put a grounding rod there, and here's your house, and lightning hits, well, lightning runs, the current runs because of skin depth radially away from the actual lightning event. It will run this way, possibly. It'll try to run into the house, but if it can't get out, well, it's not really a problem. The house is secure. Here's the dangerous thing, especially in the South. I've seen this myself. So they may have something where either there could be an arc to the ground if the current caused a significant amount of voltage, where then it would flow through there, cause a fire possibly. Or somebody could have accidentally put two effective grounds, maybe an accident. Maybe somebody had a metal pipe or something to secure something. There's a lot of ways to do this. Water lines are the worst. You know, these metal water lines, you can get it. And now current comes in here. Instead of all being shunted down there, it goes into the house and comes out. And when it goes into the house, it uses the path of least resistance, which usually means cables like coax cable that you wouldn't want. And they get into a TV and blow it up. And they do all sorts, I shouldn't say blow it up, it'll destroy it and it can cause fires. It's a horrible problem when somebody just brainstorms the best way to do, say, locate another extension on your house, and they put a metal frame and they drive metal rods into the ground, and the grounding rod's on the other side, and they didn't think anything about it, right? And now, all of a sudden, that metal stuff goes into and is secured to it's into something that is an electrical ground in the house. Now, lightning hits, comes across there, goes into the house, finds the path of least resistance, usually the wiring in the house, and kaboom. I mean, your washer gets blown out because the current wants to go back to the ground in the washer, which takes it to 2 points now, not one, and it messes up everything. I saw this firsthand, I think last year. A good friend of mine, has a house that's recently built, and lightning didn't hit it, it hit near it, maybe within a quarter mile. And their washer was taken offline, their sprinkling system, their garage door, all these devices got taken off, and somebody didn't do the right job of grounding and protecting. And anybody else got stories about this? I got a lot. A kid that sat in this class 15, 20 years ago named Paul Rye, had his father's dream home burned down because they didn't install lightning protection. It was on a hill. It has, I think, a granite slab or something like that under it. There's a lot of granite. And there were lightning hitting the trees all around. It's on a hill, dream home. Guy worked for Alabama Power. He had literally ordered lightning protection equipment. It was in his yard. And a Friday afternoon, I believe it was, I get a call from him. He's frantic. My father's house is burning down. I went out there and saw him. But it happened once, he didn't put this up. Now that house had a unique problem. Usually it's easy to get a ground rod in one location. And then if you're in an area that gets hit by lightning a lot, what you do is you take a wire, a heavy gauge wire, and you hang it up, and it's called a cone of protection. If you had gross, you may have heard of this. If you want to protect the structure, you have to be up so that if there's a 30-degree cone is formed by a guy wire that can take a lightning strike. And then you have ground rods on either side of that. It has to be electrically stout so it can take a huge amount of current. Then you won't have a problem. It'll be protected because the lightning won't hit your house. It'll hit that 99.99999% of the time. Guy had the equipment to do that, but he didn't put it up. Now this is an area where that first ground rod probably wasn't drilled deep enough, and he probably didn't have any kind of, you know what lightning rods are? Stuff like this. Go to Haley Center, you'll see tons of them. Didn't have that on there. It got hit actually near his house, and it burned the whole house. And I went out there, and I was out there, I was watching the fire department's there. I had an experience I've never paid for, never wanted again. The fire department's there putting the thing out. Man, Paul, I'm sorry, I hear. What was that? Sound like a. He had an ammo locker there. I mean, they had more bullets than they knew what to do with. And what happened? The fire got to that. And when they start going off, everybody. Talk about people moving faster than the speed of light. I've been around gunfire, but not at me. Anyway, that's a true story. See you Friday.